Welcome to the post-class video on covalent bonds and Lewis structures.
So we're getting a little wet today here with all this water.
Yeah, exactly. Bring some water in from outside. So we learned about how to draw Lewis structures of elements and just count up the valence electrons by counting across on the periodic table and put them around the elements. So we have oxygen and we have hydrogens. And when I learned about Lewis structures in high school, I remember that we actually, when we were forming molecules, we used dots for the electrons on one element, and then we used X's for the electrons on the other, so we could kind of keep track of what happens when you put them all together.
Right.
And so we have our water molecule there, right? And oxygen still has its electrons, but now we've joined, the hydrogen electrons are now being shared. Right? And so the oxygen has a total of 8 surrounding it. Each hydrogen has 2 that are right next to it, and so their valences are nice and satisfied. Right? But it kind of illustrates the sharing nature, is that the bond is formed by sharing 1 electron from hydrogen and 1 electron from oxygen.
Right.
Now, I think that this is maybe a little bit dishonest way of showing electrons.
Sure.
Why do you think I think that's dishonest?
Well, that's because the electrons are relatively not stationary. So they're not just, this electron isn't going to stay right here. They're all going to be sort of moving around.
Yeah, once you put the molecule together, who's to say what electron comes from which one? Right? So maybe a better way to represent it, more accurate way, is like this, where all the electrons are kind of equal, and you don't really know which ones came from which. But these 2 electrons are still shared between the oxygen and the hydrogen. But the electrons in the bond are actually different than the electrons that aren't being shared, right? And we call these bonding electrons, and that represents 2 electrons. And what are these called? It's all a lone.
Oh, our lone pairs.
Lone pairs. Yeah, lone pairs of electrons. So the oxygen has 2 lone pairs of electrons, or non-bonding pairs, and 2 bonding pairs, where the electrons are shared between the hydrogen and oxygen. Right? And so for simple molecules, it's kind of easy to put together Lewis structures like this. And it just describes a simple way of describing the bonding. You're sharing the electrons.
Right.
What we learned was that, in fact, the electrons that are shared between 2 atoms aren't shared equally.
Right.
Right? And this concept of electronegativity, why is that concept so important, Tyler?
Well, it tells us a lot about the ways that atoms are going to interact with each other.
Exactly. It's kind of the one periodic trend that's used and applied to molecules, and chemistry is really about how molecules relate.
Right.
It's going to tell us which side of the molecule has built a positive charge, which side has negative charge. It's going to tell us how different molecules are going to orient and line up and react together. It's going to tell us which molecules like to interact and which molecules don't.
Right.
It's really a powerful thing for such a simple idea. And electronegativity, just like the other periodic trends, is controlled by effective nuclear charge.
Right.
Oxygen has a higher effective nuclear charge than hydrogen, and so these electrons, even though they're covalent and are shared, they're not shared equally.
Mm-hmm.
And so these 2 electrons, maybe, it's not 50-50 between them. Maybe the oxygen gets 60% of the electron density, and the hydrogen is left with only 40% of the electron density. Well, that means that the hydrogen doesn't have as many electrons as it ought to.
Right.
And that leaves behind that's the Greek symbol for delta.
Right.
And it means a partial positive charge, just a little bit of a positive charge.
Right, because they don't have the 1 or 2 electrons they should have. They're having a little less than that normal charge.
Yep. And if they have the partial positive, that means that the oxygen has a partial negative.
Because he's hogging the electrons.
Hogging the electrons, right? And that's because oxygen is more electronegative than hydrogen is. And so we should probably know the top few atoms in their electronegativities. What's the order? What's the most electronegative element?
That would be fluorine.
Fluorine. And so fluorine is the most electronegative. And that's greater than oxygen.
It would be oxygen, right?
And that's greater than
Nitrogen.
nitrogen and chlorine. They're about the same. And after that is, I think, bromine. And after that are things like iodine and carbon are about the same. And then hydrogen. Right? And it's kind of important to have this order kind of memorized because you're going to use it over and over, and you're not always going to have the textbook or the workbook or a reference. You kind of need to know those.
Right.
And this is used all the time in organic chemistry, all the time in biochemistry, and so it's used in a lot of different places in chemistry. Mm-hmm. Okay, so when one atom gets more of the electrons, we say that that's a polar bond, and we can represent the polarity by putting a little, instead of a bond, we could actually draw a little arrow and put a positive at the positive end, and the arrow points where the electrons are being drawn.
I see.
So that's a polar covalent bond.
Okay.
If it gets polar enough, guess what happens? The electrons are considered to be completely transferred, and then it's an ionic bond.
Mm-hmm.
Okay?
All right.
So, I hope that helps a little bit, and we'll see you in class.